Well, thank you all for coming. So what I wanted to do here is to first of all start off by giving a general project update on the Ethereum project, where we are from a business and sort of organizational perspective, where we are from a technical perspective, what our plans are going to be going forward, and hopefully how you can get involved. So to start off, the big events that we had in the past 1.5 months is the Ether sale. So we reached 31,500 BTC, 60 million Ether, 18.4 million USD if you actually multiply every transaction by the Bitcoin price at the time of the transaction, and over 9,000 purchases. So thank you all who participated. More interesting statistics. So there, if you look at the chart of Ether purchased over time, what you see is something actually very similar to common crowdfunding campaigns, where you have a lot of people participating at the start and a lot of people at the end and a bit less in the middle. But over here, it's actually a lot more pronounced. And the other thing is that you notice like that there's that whole period in the first 14 days, and then it sort of gets flatter in the last 4 weeks. So for those who don't know, the sort of economic explanation here is that the way the Ether sale worked is that for the first 14 days, the price was 2,000 Ether per Bitcoin, and then the price increased, or linearly, or rather, and so the amount of Ether that you can get per Bitcoin reduced linearly. So it reduced linearly, so by about 21 days, it was around 1,800, then 28 days, it was around, I think by 21 days, 1,750, 28 days, 1,500, 36 days, 1337, then stayed at 1337 for the last 6 days. So most people, so from a game theoretic perspective, if you want to get in, you'd ideally want to have as high a price as possible, so or rather as low a price as possible, so you'd want to get in during the first 14 days. But it makes sense to wait, because if you wait, you have more information. You have more information about how many people already participated before you, and so roughly what your percentage is. So what we discovered is that a very large number of people actually followed the game theoretic prescription, and they waited until day 14. I think day 14 went up from like 14,000 BTC to 22,000. And then some people waited until day 15, some on day 13, and so forth. So, and then over here you can see exactly where all the spikes are. So the amount by purchase size, most of it came from people buying between 2,000 and 200,000 Ether, so between 1 and 100 BTC. Top 100 purchasers got 40.7%. So this compares to, I believe, 25% for Bitcoin, somewhere in between 55 and 60% for the more sort of mainstream altcoins. Gini index 0.830. It looks high, but actually, so an interesting point about Gini indices is that there's a difference between a Gini index for the amount of for your income and a Gini index for wealth. And so for income, on average in the world, the Gini index is about 0.55, but for wealth, it's like actually the entire world average is about 0.8. So cryptocurrencies in general don't do that badly. They're between 0.8 and 0.9 or so. So an interesting point is that once Ethereum actually launches and once people start using contracts, a lot of these statistics are actually going to be impossible to measure, basically, because all the Ether and all the other currencies are going to be stored in contracts, and if you look at a contract, it's very hard to figure out who the actual owner is. So that's actually just an interesting economic research problem, figure out how you measure statistics in the context of a Turing-complete financial system. That's actually something that I'll go back to a bit later once I start talking about proof of stake. So largest purchases, 1 million Ether, 996,000 and 933,000. I actually went back in the blockchain, and the 996,000 purchase, it was actually linked to another purchase of about 80,000. So the guy bought a bit more than a million total. The terms of service, by the way, actually limited you to 2 million, so he was actually perfectly fine doing that. So that's all we get from the statistics. So moving forward, project organizational updates. So our main development hub from here is going to be Berlin. So Berlin, basically C++ development. This is where things like the Ethereum C++ client are going to be developed, Whisper, Swarm, some economic modeling, some testing. We plan to expand to about 20 people. So currently we're living in a co-working space, but we're actively in the process of getting an office, and we should have that within a few weeks. Amsterdam for Go development, potentially other locations. So here it's looking at like Ethereum is very heavily concentrated, so there's a possibility. But then again, we'd want to try to limit the number of places that we have just for efficiency. It's good to have everyone working out of one place if we can. So protocol updates. So we've released POC 5 about 1.5 months ago. Yay, 2 clients all perfectly in sync with each other. Then it went up to 3 clients with Python about 3 weeks ago. POC 6, we created a new version of the Ghost protocol, which lets us knock block times down from 60 seconds to 12 seconds. So the basic idea is that it solves the centralization problem by letting you actually take a block and submit it and get most of the reward for it, even if you submitted the block way later after, like, say, 3 other blocks were created. So even if you're some miner and you're relatively far away, and I think actually even going up to 8 blocks, if you manage to get onto the blockchain, even if 8 blocks got submitted after you can still get 93% of your reward. So with that feature, there's a simulation script that shows that the whole thing works pretty much fine up until a single miner having about 30% hash power. So we're stress testing that particular system. POC 6, when it goes live, is going to have a 6-second block time, but in reality, we're probably going to push it back up to 12. New opcodes. So depend and swap end basically let you go deeper into the stack. So the main reason why Gav wanted to have those is basically so that the EVM architecture closely mirrors the LLVM. So LLVM is basically kind of like a generalized compilation toolkit. So if we do that, it's supposed to let us fairly easily basically just port over existing compilers for languages like C and C++ over into Ethereum. Add mod and mulmod, basically modular addition multiplication. It's useful for elliptic curve addition. Extra code size and extra code copy. So with those opcodes, what you do is they basically let you copy other contract code. So this actually provides some interesting possibilities just from a game theoretic standpoint, because actually if you ever follow like decision theory and rationality and AI research somewhat, one of the interesting problems is what happens with simple game theoretic experiments when the agents involved can actually read each other's source code. So one of the big problems is, can you come up with an AI that cooperates with itself on a single round prisoner's dilemma? So the standard prisoner's dilemma is, of course, this idea that people can either cooperate or they can defect, and if you defect, you increase your own payoff slightly, but at high cost to the other party. And so it's in the individual interest to defect, but if both people defect, they're both worse off than if they both cooperated. So in a one-round prisoner's dilemma, if you want to maximize your own gains, you'd think it makes sense to defect. But if 2 agents can read each other's source code, then it turns out that you can create some clever strategies where agents can actually cooperate in a single round. So it provides some interesting opportunities, especially once we have things like blockchain-based organizations and DAOs and AIs running on this thing for what they're going to do. Post, basically like call, except instead of executing the code immediately, it waits until the end and it executes the code after the end. Call stateless basically lets a contract call itself, but temporarily call itself using other code. So it lets you do things like abstract out certain kinds of methods that do certain kinds of modifications to your storage. That's basically it for POC 6. It's currently sort of halfway through development. I think the protocol version's at 32. Feel free to download C++, Python, and Go. Python is actually in a pretty usable state at this point. So it's any of the clients, feel free to download them, make transactions, try and at the very least sync the blockchain. And if you find an error, please tell us. So proof of concept 7 is the one we intend to do after 6. So for POC 7, one of the big things that we're planning on adding, either in 7, maybe we might have to push it to 8, but we hope not, is the consensus algorithm. So we've been working on this idea of ASIC resistant proof of work. Basically, Bitcoin relies on this hashing function as its consensus algorithm. So the blockchain, as the blockchain grows, it's basically a voting function of how much CPU power you have. But the problem with that is that it's economically inefficient because people are basically wasting CPU power. So proof of stake, ASIC resistant proof of work is our earlier effort, is basically making proof of work that's resistant to hardware specialization. So right now, for example, in Bitcoin, they have these factories producing pieces of specialized hardware that can compute Bitcoin's mining function 10,000 times faster than CPUs can. And so if you want to participate in the Bitcoin network as a miner, you basically have to have one of these devices. The result, it gets very centralized, and there's this one factory in Shenzhen in China that's actually producing 25% of all the new hash power that's being added to the Bitcoin network. Might be below 20% now since the hash power has been growing exponentially, but there's always might be some other factory popping up with 25% soon. So ASIC resistant proof of work tries to make that impossible by creating a function which is designed to be run on general purpose hardware. So that's our effort. We actually have some tests up on our mining repo on GitHub. The thing that we're adding is a proof of stake component. So we try to basically bring the inefficiency of the whole process way down. Microchains, that's this highly technical thing that doesn't really have that many effects. But if you know what it is, we might add it, we might not. Native extensions, that's something I'll talk about a bit later. Contract ABI, so idea here is that basically so one thing that we've noticed is that when people write contracts, they always write them the same way. They just write a bunch of different functions. They say, if message.data, or if the zeroth item of message.data equals 0, then do this. If the zeroth item of message.data equals 1, then do that. Equals 2, then do that, and so forth. So what we're trying to do is come up with a way to sort of standardize that, formalize it, and also try and make things more efficient in terms of the number of bytes. So it'll have support in Gav's programming language. I think he's writing a higher level language on top of LLL, and we're hoping to add support in Serpent as well. Alarm, this opcode that tries to execute code in the future. We're still figuring out how to best actually do that. So, big thing we're doing, native extensions. So this is big, it deserves to sort of have a slide of its own. So the idea with native extensions basically is, this is actually something we've been thinking about for a while, but the importance of it really sort of came to me in that big week-long visit that I had with the BitShares people last month. So basically the problem is with Ethereum is that, as an example, let's say you're trying to use Ethereum and you're trying to implement a decentralized market. So if you have a decentralized market, you have two order books. And you have an order book of buy orders, you have an order book of sell orders. Now, how do you match buy orders to sell orders? Now, in order to do that, you basically have to have a data structure that's called a heap. It's basically kind of like this tree structure that lets you either add things into the tree or always take out the item at the end. So always take out the lowest sell order and the highest buy order. And the idea is when someone submits an order, you would just put it into the heap, and when you're matching the orders, you just take the lowest sell, the highest buy, and you keep on matching them until one's no longer below the other. So now here's the problem. So you have this heap. A heap is basically a tree. So if you're a computer science person, you're going to know that trees have log n complexity. But it's a tree on top of a tree, it stays on top of the Ethereum Patricia state tree, and then that tree is on top of another tree, which is level DB. So really, the complexity goes all the way up to log cube n. So the problem is basically that we have this general purpose computing architecture, but it's not really efficient for all use cases. As another use case, I actually managed to write EC recover in POC6 code. I literally wrote the elliptic curve signature recovery method. It takes 350,000 gas. I was kind of expecting somewhere between 10 and 20, but no. So basically,
10 and 20,000.
Yes, 10 to 20,000, yeah. So the problem in all these cases is that Ethereum itself, being an interpreter type environment, introduces its own inefficiencies. And so in some cases, like business logic, it doesn't matter. Your computation takes 10 steps anyway. In some cases like these, it does matter, because this big, huge, long method here, and in just plain old Python, it takes like 1/10 of a second. And yet in Python, in Ethereum, it takes, I think, somewhere like 3 to 5 seconds. So that's, so the way native extensions work basically is you have this really complicated contract, it does this thing that we wants to be much more efficient. So what you do is we write a native version, we write a version in C++, which does the exact same thing, costs the exact same amount of gas, it basically simulates it, but it sort of shortcuts the process. So it takes way less time. So, and then to compensate for that, the fee on the gas cost of the contract is going to be artificially reduced using some mechanism that we haven't fully decided on. So the idea is that if you want to use elliptic curve signatures inside of your Ethereum contracts, you would be able to call the CC recover contract. Instead of 350,000 gas, they might cost you 1,000 gas, which is actually reasonable. And you write the contract, and the virtual machine would actually execute it quickly. It would do its own shortcut and everything as well. So one thing people ask is, well, why are we doing this? Why aren't we just adding opcodes? And the reason is that conceivably there's very, very many things that we might want to do. So one example is, so elliptic curve recovery is one, heaps are another one, SHA-256 and RIPE160. So for example, one interesting application for Ethereum is if you want to write a sort of like a swarm type crowdfunding app where people can put in Bitcoin, so not Ether but Bitcoin, and get tokens out. Now those tokens can be represented on Ethereum. So it's basically like a one-way Bitcoin to Ethereum asset exchange. You can do that, but in order to do that, what you basically need is a way of taking Bitcoin transactions and actually proving to an Ethereum contract that those Bitcoin transactions were included in a valid block. Now to do that, guess what? You need SHA-256, you need RIPE160, the hash functions that Bitcoin uses. So those are just some examples. Potential combinatorial prediction markets. I was actually just reading the paper by Robin Hanson on these this morning. Basically, it's this really complicated mechanism that lets you do prediction markets on many variables and arbitrarily complex combinations of many variables at the same time. So a lot of the time, these things are nearing NP hard to compute. So you might also want to do a native extension on that. Is basically the idea. And then, of course, there's going to be more hash functions. There's going to be SHA-4, there's going to be a Lamport-6, there's going to be ntrue. So instead of just adding more and more opcodes, we want to just add a mechanism, make it extensible, and let people add to it if they want. Yes?
I don't know if you're allowed to ask questions, but
you are.
But back on your example of the EC recover there, I'm just kind of curious why you chose 1,000. Of course, that's a wonderful reduction of 350 times.
Yep.
Is there a reason that it's not 10 or 100? I'm just kind of curious.
So even if you optimize it, elliptic curve recovery does take much longer than an average operation. Because if you actually look into this method, it involves some exponentiation, some of these elliptic curve multiplications here, some of these additions. Each multiplication is itself a loop, which involves an average of 384 multiplications plus additions. And then each of those additions themselves involves like 20 steps.
Okay.
So it's complicated.
So you're very good. I think I understand. You're just relying on the underlying complexity of the operation. There's not any overhead, for example, that you are including in your 1,000.
Yeah.
Okay.
So another issue, of course, is that we're basically price fixing a lot of these different variables, and it would be nice if we can take this native extension up pricing system and try and extend it to opcodes as well. But that's sort of, it might make it into 1.0. We might have to wait. We'll see. Yeah. basically, like the key benefit here is that we're trying to, is that right now Ethereum is useful for basically just business logic, but we want to make it useful for business logic and for arbitrary cryptographic verifications. Make it efficient, make it faster in ways that work. So, consensus. So this page, by the way, probably the biggest concentration of like cryptocurrency, crypto economic buzzwords you're ever going to see. Like try taking a picture of this and showing it to your mom. How many words do you think? ASIC resistant POW LRNAS patch with tapos. Custody mining. Is that like some kind of child labor thing? Yeah, so basically, the idea is that we're looking at using a combination of proof of stake and proof of work instead of pure proof of work as our consensus algorithm. And the reason is that first of all, proof of stake is more efficient, and second of all, it's potentially stronger because it seems most people seem to agree that it's harder to get 50% of the currency units of a currency than to get 50% of the work. So, like in Bitcoin, for example, I think the work might only, it only might cost a few $100 million, somewhere like in the tens of millions of dollars to pull off a 51% attack, whereas if it was proof of stake, it would cost you a few billion. So, the problem with proof of stake, though, is that there's this issue called nothing at stake, which basically means that if you have this blockchain using proof of stake, so the way proof of stake works is basically instead of voting with your CPU power, you vote with your ether. And the problem is, though, is that if you're trying to decide between two forks of a blockchain, with proof of work, you have your one machine doing work, and it can be on one fork or the other. If you do proof of stake, then potentially you can vote on every single one of the chains at the same time. Because there's a fork between this chain and this chain, you have ether on this chain, you use it to vote on this chain, you have ether on this chain, you use it to vote on this chain. And the economic incentives are actually in favor of everyone trying to vote on every single chain. So if everyone acts rationally, it's actually not that useful as a consensus algorithm. So, in January, I came up with this concept of slasher, which basically means that first of all, it makes the algorithm more deterministic, so you choose who votes for each block ahead of time. Then when people vote on the block and they get the reward, they actually have to wait 3,000 blocks before they receive the reward. And if they double vote, then anyone else can detect the cheating, and they can submit a transaction as proof, and they can take away your reward. So within the scope of 3,000 blocks, it basically makes the whole thing look pretty much identical to proof of work. The problem is, though, what happens if someone tries to create a fork that's longer than 3,000 blocks? So this is the long-range nothing at stake problem, LRNAS. So there's two patches to that. One is this idea of transactions as proof of stake. So transactions as proof of stake basically means that as your proof of stake mechanism, you're actually so every transaction includes a hash or part of a hash of a recent block. So it's actually the transactions that are themselves voting. So the reason why this works and the reason why this doesn't have the nothing at stake issue is that there's no corresponding incentive to try and get your transactions onto every blockchain. In fact, like after you've paid money for some product, after 3,000 blocks, chances are you might have even received the product. If there is some fork that could make that transaction not happen anymore, you actually want your transaction not to appear on that fork. You kind of want to do a chargeback if you can. So, like obviously, it would be a bit mean to do that, but if we're talking about incentives, the point is that there's no incentive to try and copy your votes over anymore. The other approach is this custody mining idea. So that basically means put a bit of proof of work on the proof of stake. So basically, the mathematical argument for why that works is that if one of these long-range attacks starts, and you assume that there's some probability less than p of that attack succeeding, then because double voting actually takes more effort, it takes a bit of proof of work, then that effort is less than your expected return from double voting. So it carries over that property from proof of work. But what it takes from proof of stake is it sort of lowers the expected probability of an attack way down, and because of that, And because of that, the incentive that you need is much smaller. So there's two models. We still haven't figured out exactly which of those we'll take. There's actually a lot of very interesting complications in involving them, because in actually implementing these, because one of the problems here is that Ethereum is as I was saying, it's in part a Turing-complete financial system. So, and in something like Bitcoin, proof of stake is relatively easy to implement because you have coins, you have addresses, and you know that people have, and you always know what the owner of any particular address is. So in Ethereum, things are going to be more tricky because first of all, you have other assets and you can't really figure out, what other, you can't really figure out whether or not something is an asset, how valuable an asset is, and so forth. Like an asset is just a computer program, and computer programs can be anything. So that's one issue. Proof of stake depends basically entirely on Ether. The second point, though, is that even if you have Ether, that Ether could be in contracts that have any kind of ownership policy. You could have a multi-sig 2 of 3, you could have 5 of 10, you could have 2 of 3 up to a maximum, and then 5 of 10 for anything else. And you could even have some kind of DApp, like a lottery. And in those cases, it's basically intractable to figure out who the actual owner of any piece of Ether is. So the way we're thinking of solving the problem is basically by adding a sign op, basically by adding an opcode that allows a contract to say, yes, any transaction that reached this point is allowed to vouch for me in this particular case. So that's basically where we're at with the consensus algorithm. It's actually getting to, this is actually getting to the point where we have a proof of stake algorithm that I'm comfortable with. There's other approaches like delegated proof of stake, which relies on voting a bit too much. Then there's, in general, basically, proof of stake is a very non-trivial problem, and it's actually surprising just how far we've come in the past year on this one particular issue. Like a year ago, we were still, Coin was basically still state of the art. Now we have transactions as proof of stake, we have Slasher, we have custody mining, we have hybrid proof of stake, that idea from Ido Bentov, we have Tendermint, we have DBoss, and transactions proof of stake was actually invented by BitShares originally, by the way. So there's this is actually getting to the point where it's close to mature technology. Whisper and Swarm. So to remind people, Whisper is like generalized peer-to-peer messaging. Swarm is like generalized peer-to-peer data storage. So the C++ library is sort of being modularized. It's being prepared for development. The protocols themselves are in an early stage at this point. But we're hoping, so it's moved on. It's not just a white paper. It's actually, or it's not just an Etherpad. Etherpad was not invented by us, by the way. It's actually starting to be coded. And what we're trying to get out of these is basically like a full sort of decentralized internet. So basically, if you want to write something like a messaging application, or even something like Twitter, you don't want to put all your messages on the blockchain because that's expensive. You'd want to send messages through Whisper. You might want to store some content, like say images in Swarm. And then if you want to say a registry of accounts, then you might want to use Ethereum for that. So that's basically sort of the general vision. Try and make as many things that are normal applications now possible to turn into decentralized applications half a year from now. Continuing paths. So right now, these are basically our priorities. Ethereum 1.0 core, so virtual machine, the low-level stuff that makes it all work. Optimization, security, virtual machine consensus. UI, we obviously want to make our interface pretty. Mobile and light client implementation, we want it to be possible to use Ethereum on phones, and just as importantly, we want it to be secure to use Ethereum on phones. So things like simplified payment verification have been on our minds pretty much from day one. Education, so moving beyond tutorials, the ideal thing to have would even be sort of kind of like a Udemy course type of thing. Learn how to program contracts, so you can follow decentralized applications start to finish. And developer tools, and of course the actual applications. So ideas for decentralized apps that you could start building on Ethereum today. These are actually all pretty much doable. So like we know how to do them, we know how to write these. So Shelling Coin, in case you haven't heard of Shelling Coin before, the idea is basically like a decentralized Oracle. So if you want to have some Ethereum contract dependent on some fact from the outside world, say you want to have a contract that sends some amount of this currency to this person if, I don't know, the Blue Jays win the next football game or whatever. Did anyone notice that I completely borked that analogy there? Basically, yeah. So the idea with Shelling Coin is there's a question: did the Blue Jays win the football game? If the answer is yes, then the answer that you as a participant would put in is 1. If it's no, then you would put in 0. So everyone would first put in a hash of the answer, and then in the second round they put in the answer. It's kind of like putting a card face down and then flipping the card. And in the second phase, the majority answer is the answer that's correct, and the majority answer is the answer that wins. So over here, because the Blue Jays apparently don't even play football, those bastards, why are they so lazy? The answer is false, and everyone who replied false gets a reward. Everyone who replied true maybe gets a small penalty, maybe not. You can do it whatever way you want, and that's it. So Shelling Coin basically lets us have contracts that have access to real-world information. Obviously, this is unproven. It's an economic idea, but what could you use it for? So for one thing you can use it for is basically to create sort of like a decentralized dollar. So the idea is you can use financial derivatives with price feeds to create an asset whose value simulates the value of a dollar at any particular time. So why do you want this? Well, price stability. In case you haven't noticed, the value of the price of a Bitcoin has dropped by about 30% these past 50 days. If you want to avoid that, then you want an asset that tracks the price of a dollar. But the reason why dollars are why we're not supposed to like dollars is because, well, fractional reserve, etc. Ultimately, there's some entity that you have to trust, and the question is, how do you have an asset that tracks the dollar in price, but that doesn't require trusting any single party? So, and then for other things like gold, for example, like there aren't really issuers of gold that are easily accessible, and potentially you could replicate anything that's an actual asset. Then the other idea is Shelling Quake, which is that name is not my idea. I'm not sure who originally made that particular screenshot. Basically, it's this idea of an insurance application that uses the technology. Reputation systems. So reputation systems are useful in a bunch of places. I know OpenBazaar, the decentralized marketplace, which is it's not an Ethereum project at this, but conceivably either they or someone like them could easily move on to Ethereum. And basically the question is, how do you tell people who are trustworthy from people who are not trustworthy? And theoretically, it's useful for social networks, it's useful for messaging, it's used for marketplaces, even decentralized governance, a bunch of different applications. Then there's sort of these different ideas on how to run a protocol or run an organization, liquid democracy, feudarchy. Both interesting ideas, both of them you can actually finally try out and implement just using code. Cloud computing, we saw Storj. Filecoin is presenting next week. I also wrote that big long blog post on, how to be secret sharing and erasure coding guide for the aspiring Dropbox decentralizer. Feel free to look that up as well. Very interesting technology in the decentralized file storage. And then also there's decentralized cloud computing, sort of like AWS type applications. You can also do those, but it's harder. Messaging, so as I said, like there's actually a lot of people that are getting interested in this, like trying to replicate things like Reddit, things like Twitter, things like Facebook on top of these distributed computer networks. So idea is that nobody runs them, so therefore, first of all, there's going to be a much lower risk of much lower downtime. One can shut them down if you like sort of privacy and not being censored and so forth. They're useful. Potentially, better privacy in certain cases. Another good application for decentralized Reddit type stuff is if you combine it with a reputation system, that instead of there being sort of one scoring system for everyone, everyone could have their own different scoring system. So say if I as a person just like, you know, some technical discussion, and then someone else might prefer some different kind of discussion, some third person might want cat pictures, then there were, you know, we would all have our different scoring systems, and different people would see different people would weight other people's upvotes differently, and so we'd all see content that's more relevant to ourselves. Social networks, forums. You know, for a community that really cares as much about decentralization, it's interesting that we're still all on Skype. Maybe, hopefully, in the next 6 months, we'll see a practical alternative to that. Oracle systems. So for Oracle systems, there's really two things you can do. One of them is a sort of more corporate model where, say, for example, if I want to have a contract that's dependent on, or one use case is something like a key recovery. So if I have a wallet that's holding a huge fortune in either Ether or some Ethereum-based token, the question is, how do you protect that? Now, if you have just one key, then you could lose it. That key could get hacked. Even if you have multiple keys, it's sort of a bit tough to rely on. So one approach is basically to replicate the functionality of the banking system. So what the bank does is the bank holds on to basically the bank holds onto your keys for you, and they do whatever checks they need to do to verify that you're actually yourself before they let you withdraw a really huge amount of funds. So the problem with the banking system doing that is, of course, that there's a single point of failure. It relies on one entity. But with Oracle systems, we can sort of decentralize that functionality somewhat. So you could do something like a 2 out of 3 or 4 out of 8. So you could pick either 4 out of 8, say, sort of like professional entities that would actually do some work to verify your identity. So one of those entities might just specialize in, checking if you still have your cell phone. One of them might verify your passport. One of them might do some kind of face-to-face communication and so forth. And so the idea is that the whole scheme would sort of would be very resilient against any part of it failing, against any part of it being malicious, against any part of it shutting down. So, the hope is that if I have my funds in this thing, then tomorrow I die, and then because I managed to sign up for Alcor before, then I get frozen and cryopreserved. And then, the year 3000 comes along. By then, all the big banks have fallen, and some new ones have risen, they fall, and new ones have risen, and so forth. And I wake up, and because the whole thing's decentralized and it's resilient, as it turns out, at least maybe let's say 1/4 of these oracles survives. And I just go to those particular oracles, I prove to them right, the thing I forgot to say is that there's advanced medical technology, which is why they managed to wake me up from cryopreservation. But the idea is, I wake up and there's maybe just a few of these oracle entities still survive, but I go to them, I prove my identity, they check, oh hey, this guy's DNA is exactly the same. Oh, the passport seems to belong to some government that's been dead for 850 years, but all the other checks pass. And you say, okay, that's him. And they all release the coin, they all release the Ether or whatever tokens, and I have all the money that I had a millennium ago. So that's the story. So the two strategies, as I was saying, corporate is one of them, so sort of a professional entity, and the other one is social, which basically means, well, the best people at recognizing that you are actually your friends. So, well, friends, employers, family, and so forth. So if you rely on a big collection of them, then it's just another strategy. It might be cheaper. It might even be more likely to survive in a lot of cases. So, and there's a whole bunch of other examples. Like there's obviously all that you just fit on one page. So how can you get involved? So core development. We have clients in C++, Go, and Python. SHH and BZZ are the semi-official 3-letter codes for Whisper and Swarm. Developer tools, education. We need people to help write developer tools. Community outreach. Research is actually a big one. So if you have thought a lot or wants to start thinking a lot about consensus algorithms or scalability algorithms or any of the other hard problems of cryptocurrency. That's a document floating around on our wiki. There's issues like identity, there's issues like useful proof of work, there's pretty much all of the major problems that any cypherpunk should have thought of at least once are probably on there, and applications. So this stuff. So finally, this is sort of the section where I want to ask everyone, basically, how can we help you? So at this point, we have funds. We're scaling up our operations fairly quickly and substantially. We have our office in Berlin. We want to have some annual presence here. I think it's pretty obvious that the whole Silicon Valley Ethereum community is great. So congrats all. One of the biggest meetups I've seen. So lots of interesting projects too. So the things that we can do is we can either hire people full-time or part-time. We limited slots, obviously. Another thing we can do is support external projects. So one of the ideas that we've had, and one of the ideas that actually a couple of groups have been enthusiastic about, is this idea of coming up with some kind of co-working space for Ethereum plus Ethereum projects, plus potentially even just wider crypto 2.0 projects. So, is it going to be just a co-working space, or is it going to be a co-working space plus a house? We've pretty much decided that particular choice is just going to depend on what kind of people are interested, and we'll just cater to whatever people's needs are. Prizes, bounties, grants, etc. Yes, we do have a budget for supporting meetups, and we're basically currently exploring options, and this is an area where basically we want your feedback. If you're interested in any of these things, then feel free to reach out. Even send some kind of formal application if you're daring. If you want, Chris, feel free to send around my email after that.
Okay.
Yeah. And that's all for the presentation.